For my next trick, we've got an inclined plane with a pulley. We're removing friction this time, but you never know what's going to happen in the future. So we've got this smooth surface. We have our 10 kilogram block still up here, but now it's attached to a pulley. This is a massless pulley and a massless string. So we know, based on what we've looked at previously, that means that the tension throughout the pulley is the same. Now, we're asked to find what's the acceleration of the 10 kilogram block on the right. So we are trying to find the acceleration of this one. So let's draw a free body diagram of it. We've got our normal force going this way, Fn. We've got our gravity force going straight down, weight. And now we have this new force, which is a tension force pulling straight up this way. Our normal force we found before was 84.6 newtons. That's because in the y direction, our F net in the, or I guess the new y direction, is equal to 0. And as we break down our weight component, we have this weight perpendicular and weight parallel. So our normal force minus our weight perpendicular is equal to 0. So normal force is equal to weight perpendicular. And we should remember the two equations that will always hold true. Weight perpendicular is mg cosine theta, and weight parallel is mg sine theta. So this is equal to mg cosine of 30, which is 84.6 newtons. All right, now our weight parallel component here, this is mg sine theta, which is equal to 49 newtons, because we've got 100 or 98 as our mg, and sine of 30 is 1/2, so we have 49 newtons. So the question is, what's the acceleration of the 10 kilogram block on the right? Well, we have to think like this. The 10 kilogram block is being pulled up by the tension, and this tension is going to be the same throughout here. So if we think about this as a tug of war, we've got pulling this way 49 newtons, and then overall for the whole system, we've got pulling this way 98 newtons. So to find the acceleration of the 10 kilogram block on the right, we have to find what the net force is of the entire system, because the net force of the system will be equal to the mass of the system times the acceleration of the system, and the acceleration of the system equals the acceleration of each individual block. So equals A1, which equals A2. So think of it as a tug of war, 98 newtons pulling this way, and 49 newtons pulling this way. So our net force then is 49 newtons. We have 20 total kilograms of mass pulling, and multiplying that by our acceleration ends up giving us an acceleration equal to, the result is that our acceleration is equal to 2.45 meters per second squared. And that's our acceleration, and it's going to be up the ramp, because the hanging mass is pulling with more force than our ramp's mass is pulling down. The next question says, what hanging weight would allow the system to be in equilibrium? Well, we know that we have 49 newtons pulling this way, so we need to have then 49 newtons pulling this way in order for it to be in equilibrium. So therefore, if we have 49 newtons as our weight, that gives us a mass equal to 5 kilograms. Question 7 asks, would our answer to question 6 be different if the coefficient of static friction was 0.5? And the answer is yes. Static friction would allow us to have more force pulling this way, or more mass pulling this way, in fact. So we want to think about it like this. Static friction would then pull down the ramp, and our static friction force would be equal to our coefficient of static times the normal force, which is 0.5 times 84.6. So that means that we can have a maximum static friction force of 42.3 newtons. So now that we have an additional 42.3 newtons pulling this way and 49 newtons this way, we can in fact have a total of 91.3 newtons of weight. right? Whereas before we could only have 49 newtons of weight, now we can have 91.3 newtons of weight, and 91.3 newtons of weight gives us a mass equal to, because weight is equal to mg, so mg equals 91.3, and so then our mass can equal 9.31 newtons. Sorry, kilograms, not newtons. Kg. And the final question is, what coefficient of friction would allow the above system to stay at rest? This is referring to the very top one. We had a deficit of 49 newtons, so we need our static friction force to be equal to 49 newtons, which will equal our 49 newtons, which will equal our coefficient of friction times 84.6, right? Because our coefficient of friction is going to be multiplied by our normal force. So with that being the case, we need to then have a coefficient of friction equal to 0.57. Now, interestingly, that is the same coefficient of friction that we found in class. The difference is that this static friction force is going to be preventing us from sliding down this way. So our static friction force, our static friction force is going this way, so it's going to be preventing us from sliding up this way. So this is the direction of our intended motion, and we are pulling the opposite direction. So in class, we had our friction force pointed up the ramp. Here, we have our friction force pointed down the ramp, preventing us from falling over the top of the ramp.